4.3 is over geometric sequences, not series. We're going to learn about series later. Sequences. So again, we talked about arithmetic. Arithmetic is just another word for linear. Here, geometric is just another word for exponential, multiplicative change. So let's say I'm looking at a series here, or I'm sorry, sequence. 7, 14, 28. I have a constant multiplicative difference of 2 with an a sub 1 equal to 7. So is it arithmetic or geometric? Well, it's geometric, multiplicative change. Here's another one, 2, 18, 162, 1458. In this instance, I have a multiplicative change of 9. So that also makes this geometric. Now let's say I want to write a recursive function or equation and an explicit one for this one. So let's say I want to do recursive. Well, each term is found by taking the previous term and multiplying it by 2, where my first term was 7. Now over here, let's come down here and do recursive on this one. I have a sub n equal to a sub n minus 1, and I'm multiplying by 9, and a sub 1 is equal to 2. Cool. So there's different ways that we have done explicit functions here for exponential. We can do a sub n, or my output is found by taking my growth, my multiplicative change, however you want to write about that, like our growth factor, and raising it to the nth power times my 0 term. So that's one way of writing explicit functions. We're going to look at another one down here in a few minutes. But let's say I did use this one. This one would be that my a sub n and my growth factor is 2, and I raise it to the n, and then I need to find what my initial term, what my 0 term was. So if I've been multiplying by 2 to get from step to step to step, I would undo that, and the only way I can undo or use an inverse operation of multiplying by 2, you can multiply by 1/2, which would give you 1, or you can divide by 2. Either instance here, 7 divided by 2 is 7/2, or 7 times 1/2 is 7/2. So 7/2. Here, my output is found by taking my growth factor of 9, raising it to the nth, and my a sub 0 would be 2/9. That's one way of doing these. We'll look at a different way down here in just a moment. So the definition of geometric. Recursively, it's a sub n equals a sub n minus 1 times r. This is our common ratio. So watch out for that. That's a word you will see when you do your DP test. Common ratio. Just like on the last one, it was a common difference. Here we're looking at common ratio, or my consistent multiplicative change from step to step. So a sequence, a sub 1, a sub 2, a sub 3, is geometric if there is a constant r for which all integers where n is greater than 1, r is called a common ratio, where that number r, or that multiplicative change, can be found by taking a term and dividing it by its previous term. So for instance, if I took 162 and divided it by 18, I would get 9. If I took 18 and divided it by 2, I would get 9. If I took 2 and divided it by 2/9, I would get 9. Hence my r is 9. So explicitly, a different way that we can find our formula is that we can say our output is found by taking our input of the output of the first term, multiplying it by the common ratio raised to the n minus 1. Well, would that look different compared to this? So let's say I was looking at this one right here. I could say that a sub n is equal to a sub 1, which was 2 in that instance, times 9 to the n minus 1. Well, would it output the same thing? How are these the same? Well, n minus 1 is the same as 9 to the nth times 9 to the negative first. Well, 9 to the negative first would be the same as multiplying it by 1/9. So I would have 9 to the nth times 9 to the 1, times 1/9 times 2. And then these terms right here would become the 2/9. So you can see that this explicit equation creates equivalent outputs to this equation because these two equations are equivalent. Okay, you don't need to simplify this out. I was just demonstrating to you that these two are indeed equal and that this can be easier when I know the a sub 1 than going back and trying to figure out the a sub 0. So both of them work to help us write explicit equations for geometric sequences. So what are some applications of geometric or exponential series sequences? So compound interest, whenever I'm like buying a house or buying a car, the interest compounds from step to step to step, so you're paying interest on the interest. Medicine losing effectiveness, that's a decay where there's only a percentage of the previous amount in your system, like 75% of the previous amount of the drug may be in your system, so they can use that to calculate out when they need to redose. If there's an invasive species like a plant or a weed in a lake or a community, you can see those growing exponentially. Also, like I think the little mollusks that come in on boats would follow an exponential rate. Climate change is another example of exponential change. This says epidemics. It looks like it says epidemis, but it says epidemics. So a virus will travel at an epidemic rate where each person affects a certain number of people, and then each one of those affects a certain number of people. So you can see that it would be branching off in an exponential way. The probability of an event occurring, like flipping a coin. Let's say I want to flip a coin 50 times. What are the odds I'm going to get 50 heads in a row, something like that? So you could say it's 1/2, and then 1/2, and then 1/2, and each one of those would be branching off. Or you could just find your sample space, that you would have a certain number of options, 2, when you flip a coin, raised to the nth. So the number of outputs would be 2 to the number of times I flipped it. And then also population growth, like if you're growing at 5% from year to year, so you would have 1.05 because there's 105% of the previous years, and then time your initial population. So that would be another example. So we're going to look at compound interest here in just on the next video.